Welcome back to thermodynamics, or bionics of surfaces as we like to call it. We were talking about quantization last time, so we'll just continue in that theme. So we would like to see why it does it and where it does it, or more importantly, can we get some evidence that it really exists. There I will send you to watch my video of a reaction. What happens in the reaction? I've got some chlorine, CO2, and I've got some hydrogen, H2, and you can mix them together and nothing happens. The reaction doesn't start. So something is preventing the reaction from starting, and the reaction forms two hydrogen chloride molecules and gives out a lot of energy. It gets up to a few, 1,000 degrees-ish. It's not super high, but it's hot. If we do this reaction, it's fairly energetic, it's fairly robust, and it usually explodes, which is one reason for doing it. It's kind of fun. But the interesting thing about this reaction is that we can set it off not only by heat, but also by light. If we take hydrogen and chlorine and we heat it up, the usual way of heating it up would be to put something hot in there and it sets it off and it goes bang. It's quite a reactive mixture, and when it starts to react it gets hotter, so it usually runs away and causes an explosion. We have to heat it quite hot to get it to do that. It's perfectly stable at room temperature, but we can get it to go off by shining light on it. If we shine light on this hydrogen, we need ultraviolet light, very harsh light, to get the hydrogen to react. So if we take the equivalent reaction with hydrogen and oxygen, it's hard to get that to go by shining lights on it. But if we take chlorine, chlorine is not so strong, and what happens is we can excite one of these electrons that's in the bond. So we've got a bond that contains two electrons. It's not a division sign. It's two electrons in a bond, and if we kick one of these out, it goes into a terrible state. The terrible state that the electron goes into is an anti-bonding state, which means it sits out here and pulls the molecule apart, because there's only one electron holding it together and one electron trying to pull it apart. The molecule typically falls apart at this point. But how much energy does it take to do that, and why does that matter? So it takes a certain amount of energy to do this, and the light is special. We can deduce that because it always takes a certain color of light and no less, then there is something special about light. It must be in some kind of wave packet, in some kind of discrete amount, and deliver that amount of energy to our molecule, and the molecule then gets to choose what to do with it. So if we shine red light on this, nothing happens. If we shine yellow light on this, nothing happens. And if we shine green or blue light or ultraviolet light on it, it explodes. This reaction happens. It makes the chlorine break up into a chlorine with an arm broken, and another chlorine with an arm broken. It's got one electron. It's not charged. It's a chlorine atom, effectively. And it's really, really reactive. And those chlorines could find each other, but they could also find a hydrogen. If they find a hydrogen, they come along, so let's have our H2, and they react with this hydrogen. So let's have this one react with the hydrogen, and it does that, taking one electron out of the bond, and that forms a new thing. So we've made one HCl backwards, but it's this. This is an HCl, it's just ClH, and this is an H with a dot on it, which is a hydrogen atom. Hydrogen atoms are also really reactive, and that can go and find a chlorine and react with that, or it can find a hydrogen and just hang around with it, but it's fairly likely to find a chlorine and react with that, and that will keep our chain going. You can see that we're not getting any more or less things. It's not a runaway reaction like a nuclear reaction, but making this hydrogen chloride makes heat, and if we make enough heat locally, we can set off the reaction by it being hot. And remember, if we cause this reaction to happen, we can calculate from thermodynamics how hot it should be, and as I said, it's well over 1,000 degrees. It's hot enough to cause the reaction to happen. So we have got this process, and it's interesting because of the colours that we can put in. I haven't got the pens to do it. If we put in different colours, there is a threshold colour that is required to make this reaction go. That's interesting because it is a fundamental discovery. Because if we imagine a wave on water, so if we imagine a wave on the sea, not a tsunami, but a normal wave on the sea, just coming at us continually, if we want a certain amount of energy from that wave, all we have to do is build a wider collector for the wave, or wait longer. The chlorine doesn't appear to be able to do those things. So if red light is coming along, it doesn't appear to be able to wait and get more of the light, because then it would explode. It has to do something with the energy that it has. More interestingly, if we look at our chlorine molecule, we can see that it's also coloured. It's coloured because it's absorbing some visible light, so it actually appears a nasty green colour. If we give it really, really, really bright light and we bundle it very close together, then we can discover a new thing, that sometimes we can get the chlorine to actually absorb wavelength of light that's twice as long, or energy that's half as much. So if we give it half as much of energy by changing the colour down, we can get it to do it, but it's way more difficult than we imagine it should be if we're thinking of the sea and waves on the sea. So we have to change our thinking to quantization, so we can imagine a particle of light or a package of waves, like a section of wave coming, and the chlorine can decide to absorb it or not. Obviously, it doesn't really think. But if it absorbs it, it then has to do something with the energy immediately. It has to go somewhere. There has to be some kind of energy level, some kind of space for it to go in. As we saw from the last lecture, the last subject, with hydrogen floating around, if we have energy levels, rotational energy levels, we have to get enough energy to be able to activate one, to be able to turn it on, before rotational energy levels play a role. And likewise, these are vibrational energy levels equivalently. We want to give it vibrational energy. They're not. They're electronic energy levels. Let me correct that. These are electronic energy levels, and if we give it enough energy, we can make it jump up. But here, it would be very hard to do this with temperature. We would be very hot indeed to be able to make this electron jump into this other orbital. But if we take light, it's easy. We don't even need that much light. It's only green. We can connect this to the theme from last time with this type of experiment, this Fermi's famous experiment. We have a metal down at the bottom, and we apply a negative voltage to it. We have a metal up at the top, and we apply a positive voltage to it, and ideally we suck out all of the air to stop air getting in the way, so there's nothing in here. And then what we want to do is make the electrons flow. Last time we had a valve, a thermionic valve, so we heated up this plate, and that meant that the electricity only went in one direction. It's not a very high current device, obviously, because we've got electrons flying through space, but it's a way of switching something on and off, just by ensuring that one of the two electrodes is hot and the other one is cold. We can do it a different way, however. If we take a light, so let's draw the light like this, a normal light bulb, and we shine it on here. So we want a hot light bulb so that we can get different colours out. If we use an LED, we get specific colours out, and we want, for our thought experiment, to have all colours. So we want just a hot filament in here that's glowing white hot, so that we can have all colours of light that we want out of here. Then we put obviously something in the way and choose what colour we're going to have. If you do this experiment, and I have, I'm not sure you do it in our physics labs, but it's a fairly common physics experiment. You apply a voltage here, so we've got colour here, which is wavelength. Let's have 1 over wavelength, because wavelength gets longer, the energy goes down, and it's not linear, it's reciprocal. So 1 over lambda, 1 over the wavelength, is actually linear in energy, is a better unit. If we apply 1 over lambda, so we change the energy of light that we're putting in, we discover that we get some kind of step, and it's almost flat at the top. It's a bit difficult because it's hard to get the same power output of different colours from our light. But we get a relatively sudden turn on of our current. Let's put current I. This is an ammeter. We measure current in amps, so we're measuring current in amps here. I is current. If we cool our electrode down, it obviously requires more energy, because the electron here has a combination of the thermal energy, the electrical energy, and the light energy. So it's hanging around near the surface, kind of bobbling out and trying to escape, but it can't quite escape because the atoms, the positive charge of the electron, of the metal atoms, it keeps pulling it back in. So if we have whichever way around I had it, if we cool it down, it has less energy, and so it requires more energy from the light, and so it shifts it up here. And if we heat it up, it has more energy to start with, and so it is easier. We don't need such a blue colour. This is blue up here, this is red down here. It's the way around for energy. The amount of electrons that come out are dependent on how bright the light is, so we can also turn it up determined by how bright the light is, but it is also the same as the last experiment. I didn't take this, or demonstration or whatever, so thought experiment. It's the same. If we really measure this, it doesn't matter how bright our red light is, until we get it extremely bright and get 2 light photons to hit 1 electron at the same time, we don't see any current at all. Obviously there is a background current because things happen, radiation happens, cosmic rays happen, so in reality there's a little background current, but theoretically in the world of perfect physics this would be 0, and we would see a sudden jump and they would all be the same height. In reality, obviously, there are things that happen that make it a lot more complicated, but this demonstration is relatively simple, and it is Fermi's original demonstration of quantization. This was discovered when physicists tried to predict what colours would come out of a hot, what they call a black body radiator, so a perfect hot thing. What colours of light would come from that? So we've got something in there that's oscillating and is giving out different frequencies of light, and they came up with a frequency that would say, okay, we can divide the energy between all the different possible frequencies, and we end up with an equation that defines relatively well what happens down at low energy. So this is 1 over lambda again, the energy. But the problem is that although the number of light, the amount of waves of light that come out goes down as we go up in frequency, the energy keeps getting higher and higher. They call this the Ultraviolet Catastrophe. So this shape is very much like the real shape that we get. So if we measure it down at red, infrared, green even, we see very much like the sun emits, and like we would see if we get a light and we put it in a black box and we look not directly at the light, then we see exactly the same thing. So we can predict what goes up, but when we get to high frequencies, something happens that cannot be explained by, or could not be explained at the time, because they were imagining that you could do the same as you can in the sea. You could just wait for a really long time and collect energy from different waves. The problem being then that the very, very long or the very, very short wavelength waves, in this case, the very high energy ones, will take more and more energy, and the thing would emit infinite energy, which is a problem mathematically, because if it emits infinite energy, then if we go back to our laws of thermodynamics, it will run out of energy pretty much instantly, and so then we'll have a problem. Also, we don't all die from all the ultraviolet radiation coming out of the sun, which we would have done already in that case. The solution to it came from Planck, and that was to quantize the energy. So you say the black body, the thing that's heated, that's hot and giving out energy, can only give out one photon at a time, and the photon has some amount times the amount of energy in a wave. So it has a certain number of waves in it, and that is what it has to have. It was entirely arbitrary at the time, so very much like the rules of thermodynamics, which are also, as I mentioned last time, determined empirically, so measured results and then tried to fit them, rather than from first principles. This is the same. They had this problem and came up with a suggestion, but without knowing exactly what. It's the same with Darwin and evolution, or Mendel and chromosomes and genes. They didn't know what it was that they were discovering. They knew, something is changing. So in the case of Darwin, something is changing. The species are getting different over time, and it seems to be random because it takes a long time and they get better for their environment. If the environment changes, those ones die. If we have Mendel's equivalent, we have something that is behaving in a weird way in pairs, and we've got this power of two relationship of all the offspring, and so we can have a dominant and a recessive gene usually, and they are usually independently inherited. That was what he discovered, but he didn't know that they were on chromosomes and that it is genes that are doing it. He didn't even come up with the words, and neither did Planck come up with some of the later consequences of his discovery, invention, or even just a suggestion to fix the maths to get it to work. What we see with our black body is that the amount of radiation coming out goes back down again and gets very close to zero fairly quickly. It has to get very close to zero very quickly, because if we have a quantum of very, very short wavelength radiation, it contains an awful lot of energy. What is interesting about that is that it took further development before we got anywhere close to where we are now. And for our subject, what is interesting is that it gives us a cutoff between things that happen as a statistical randomness and things that are that happen quantized. So if we imagine going back, or if we go back to the example that we had last time of particles in a box getting hot, so there were gas particles, they're moving around, behaving as if they're hot, and then we just choose for them to all go in one direction, then they behave as if they're cold. That seems random and stupid, and this is effectively it was the subject of a lot of conjecture. But if we choose a very small number of particles, we can see that they aren't going to behave as a normal thermodynamic system. If we take a single molecule, we cannot use normal thermodynamics to describe it very easily. We can describe the energy levels inside it, but we can't describe its motion. If we choose temperature as what we want to measure, we can't really measure the temperature of two particles or two molecules. We can't do that because we don't know what their speed is, or their average speed relative to each other, and what happens if they hit something. It becomes a badly defined measurement. It only really is significant when there are enough that it behaves statistically that we can say, okay, they're moving randomly. This is the same problem as happens in homeopathy, that as we dilute our liquid, do we have a solution of some magic cure for something, poison as it usually is called in homeopathy. So we take our drug or our poison and we start to dilute it. It behaves as if it just gets half the concentration, and we can just imagine it getting more and more dilute. And if we consider there to be infinitely many particles in there, or just to be a colour getting lighter and lighter, or whatever you want to think of it as, then you can imagine it gets less and less concentrated, and that's why homeopathy arose, before we realized that the molecules in there are of a certain size, and when you dilute it below a certain point, even if we have 10 molecules in there, for example, if we dilute it to only having 10 molecules in there and we throw away 9/10 of it, the probability that we have exactly one molecule in the bit that we have left is not very high. So as soon as we get down below a lot, we end up with a problem that statistically randomly we're going to have some of our samples will have 2 in, some will have 3 in, many of them will have none in. And then what happens when you dilute it further? When you dilute it further, most of them will have none in. And then we don't have a molecule in each one, we just have a probability that you will find one molecule in each one. This is the same with our hydrogen chloride. Obviously it is different if we shine one photon onto one atom of chlorine. Then we can determine the probability that something will happen, but we can't really say what will happen. If we shine a certain amount of light into a large volume of chlorine, then we can say, if it's enough, we can say how much it will take to cause it to explode, whatever, 90% of the time. Because there are a lot of molecules of chlorine in there and there are a lot of photons, then we will be right. But if we only have one, it might last forever. It's Schrodinger's cat.